In the previous lecture, we defined a map of sheaves the differential from the sheaf of exterior I omega to exterior I plus 1 omega, and this was first defined on coordinate open sets u, x1, x2 and so on to xn, and then we checked that du is equal to du prime on u intersection u prime. So it sufficed to check that du of the differential form f dxi is equal to du prime of the differential form f dxi. And if y1, y2 up to yn are the coordinates on u prime, then computing du prime f dxi using definitions leads to a very ugly computation. To apply the definition, we will have to write omega first in the coordinates yi's, so that will look like L equal to 1 to n dxi1 by dy d by L wedge dot wedge summation L equal to 1 to n dxir dyl, and then we will have to expand this out and write it as cardinality j equal to r g sub j dy sub j, and then apply du prime. However, we avoided this computation by checking that du and du prime satisfy two properties. And then we use those properties. So this is one remark which I wanted to make. So let X be a smooth manifold. The de Rham cohomology of X was defined to be the cohomology of the complex zero gamma X omega 0 omega gamma X where n is the dimension of X. Before we proceed, let us see two examples. Example 1 is let X equal to R. Then we know that omega is the trivial bundle and exterior I omega is 0 for I greater than 1. Thus, the de Rham complex is 0 we have t to 0. So here every f goes to df by dt dot dt. So here Ox is the sheaf of smooth functions. On X. Since R is connected, we already saw that H naught XR is equal to R. Moreover, given any smooth function G, an element of gamma X over X, we can define f of t equal to integral 0 to t g of x dx. Then f satisfies df by dt is equal to g. So what this shows, this shows that the map D is surjective. This implies H1XR is equal to kernel of D1 by image of D0. So this is actually D0 and D1 is just map 0 because there's nothing over here. And since D0 is surjective, this shows that H1 is 0. The second example, which is more complicated, is that of S1. More complicated and more interesting. So, and being given the smooth structure using the covering map R to R mod Z, as we had seen before. We already saw that the tangent bundle is trivial. We shall modify that argument a bit. For the purpose of this example. If U is a small interval in R and V is equal to pi of U, then pi from U V is a diffeomorphism. And so we have pi tilde. So this is omega R restricted to U, pi tilde, omega S1 restricted to V. This pi is a diffeomorphism, and pi tilde is a diffeomorphism. Which is a linear isomorphism on the fibers. We have a canonical smooth section of omega R to R given by S of P is defined to be dt at P. Using the identification omega R at P, so pi tilde is a linear isomorphism, omega S1 at pi of P. This defines a map of sets from R to omega S1. So we denote this map of sets by S tilde. One easily checks that S tilde is smooth. In fact, locally, S tilde is equal to pi tilde inverse compose S, and that S tilde of P plus N is equal to S tilde of P. This shows that S tilde descends to give a section of omega s1 to s1, which we shall denote by dt. This notation is justified since under the identification by tilde, the dt on u is identified with the dt on v. This gives a nowhere vanishing section of the cotangent bundle of S1. The cotangent bundle is trivial. So in particular, the de Rham complex once again looks like 0 xox xox to 0. And there is a differential which we had defined locally earlier, but now we shall give a slightly different description for it. So let us define a map P prime from gamma xox to gamma xox. So maybe I should write gamma xox times dt to 0. As follows. Let f from S1 to R be smooth. Then f compose pi from R to R is smooth and periodic. This implies that when I take the derivative of that, is smooth and periodic. And so descends to a smooth map. Let's call it d by dt of f composed by tilde from S1 to R. Or instead of calling it tilde, let me call it d by dt of this sub 0. So define d prime of f to be equal to d by dt of f composed pi sub 0. So it is immediate that this agrees, that d prime agrees with d. So recall that d was defined using local coordinates, and one checks easily since the local coordinates on S1 and R are the same. that T prime agrees with T. So we are now ready to compute H1 S comma S1. So how do we do this? So first define a linear map from gamma OX XOX to R given by G maps to integral 0 to 1 G compose pi of x dx. So we claim if G is in the kernel of this map, the kernel of this map, then G is in the image of T. So let us prove this claim. So the idea is to define f of t to be equal to integral 0 to t G compose pi of x dx. So since G and pi are smooth, this implies f is smooth. So let us check that f is periodic. So f of t plus n is equal to integral 0 to t plus n G compose pi of x dx is equal to integral 0 to n G compose pi of x dx plus integral n to t plus n now since G so this we can break up as integral 0 to 1 plus integral 0 to 1 to 2 and so on, and each of these integrals is 0 because so all the since G is periodic, integral I to I plus 1 G compose pi of x dx is equal to integral 0 to 1 G compose pi of x dx, and this is equal to 0 since G was in the kernel. So this implies that f of t plus n is equal to f of t. And I mean here once again we have used the fact that G compose pi is periodic to say that f of t plus n is equal to integral n to t plus n compose pi of x dx, and this is equal to integral 0 to t. This is equal to f of t. So this implies that f is smooth and periodic. Moreover, d by dt of f is equal to G compose pi. So since f is smooth and periodic, we can say that f is equal to some f0 compose pi And what this says, so df by dt is equal to d by dt of f0 composed by. So when we work through this definition here, this actually means that, so this implies that d prime of f0, which by definition was d by dt of f0 compose pi, and then we the descended function to s1, that is equal to g. So this implies that g is in the image of d. So next, so clearly the constant function is not in the kernel. Thus, we may write k direct sum r, there's an isomorphism to gamma xox. So if the image were larger than k, then it would contain a non-zero constant lambda. But this was this will force that there is a smooth periodic function f from R to R such that d by dt of f is equal to lambda composed pi, which is just lambda. But this will imply that f of t is equal to lambda t plus a, which is not periodic. Thus, this is a contradiction. This is a contradiction. And so the image is exactly K, the kernel. So since H1 XR by definition is kernel of D1 by image of D0, this is equal to gamma X OX by K, which is equal to R. And moreover, the image of every one form GTDT is precisely given by integral 0 to 1 by x dx, or ddt, sorry. So what we are trying to say is kernel of D1 to H1 XR is equal to R. That's his map. And kernel of D1 is all of gamma x OX dt. Since D1 is just 0, and given this is a description of this map. Okay. So this concludes, let me just add that since S1 is connected, we have already seen that H0 S1R is also isomorphic to R. So so the de Rham cohomology groups, the de Rham cohomology carries a ring structure. So let us describe that. The wedge product induces a multiplication on cohomology. A class in HIXR is represented by omega, a global I form, and a class in HJXR is represented by a global J form So we claim that T of omega wedge eta is equal to 0. So that's easy because T of omega wedge eta we saw is T omega wedge eta plus minus 1 to the I omega wedge T eta, and both these are 0 since T omega is equal to T eta is equal to 0. This shows that omega wedge eta defines a class in Hi plus j. But we need to check this is well defined. So if omega prime and omega represent the same class, then this means that there is some theta such that omega minus omega prime is equal to d theta. Then we have omega wedge eta is equal to omega prime plus d theta wedge eta is equal to omega prime wedge eta plus d theta wedge eta. But now d theta wedge eta is equal to d of theta wedge eta. So this implies omega wedge eta and omega prime wedge eta represent the same class. Similarly, we can show that if eta and eta prime represent the same class, then omega wedge eta is equal to omega wedge eta prime. So thus omega wedge eta so this implies the multiplication is well defined. And because of the properties of the wedge product, this multiplication satisfies omega wedge eta is equal to minus 1 to the power degree of omega times degree of eta into eta wedge omega, where omega and eta are homogeneous. So I can write ij eta wedge omega. So we can ask several questions about the Diram cohomology ring. So suppose f from x to y is a smooth map. Then there is a functorial map ring homomorphism these rings are finite dimensional. Vector spaces the May-Vitoris sequence Homotopic maps induce the same pullback on cohomology. Can we write the cohomology ring of x times y in terms of h star x and h star y? The cohomology ring of a fiber bundle in terms of the cohomology of x and that of the fiber. Of the fiber. So we will try to answer these questions one by one. However, let us begin with some operations on vector bundles. Some more operations on vector bundles. Let f from x to y be a smooth map. And let e to y be a vector bundle. Then we can define a pullback bundle on x which sits in a diagram f upper star e. There is a map f tilde. F tilde is a smooth map and f tilde to e restrict to f of p between these fibers is a linear isomorphism. So let's try to see how to define f upper star e. So suppose y is a union of vi's is an open cover and E is obtained by gluing trivial bundles over Vi using transition functions phi ij from Vij to GL and all. So then we let ui be equal to f inverse vi. Then x is the union of ui's, and uij is exactly equal to f inverse vij. Thus we have maps phi ij compose f from ui, uij to vij to gl and r. It is trivial to check that these satisfy. Trivial to check that these satisfy the co-cycle condition. Thus, these transition functions can be used to glue the trivial bundle on ui along the uij's, and the resulting bundle is denoted f upper star e. So let us now define the map f tilde. So on ui, f upper star e is trivial, and similarly, and e is trivial on vi. So define f tilde by ui cross rn, and f takes ui to vi, and this maps to vi cross rn. So the map is given by x comma a vector lambda gets mapped to f of x comma lambda. So we need to check that these, so let's call this fi tilde glue together. So suppose x belongs to ui intersection uj, then f of x belongs to vi intersection vj, and we have the following identifications: x comma lambda in ui cross rn is identified with x comma pi ij compose f of x of lambda in uj cross rn. And on the other hand, f of x comma lambda inside vi cross rn is identified with f of x comma phi ij of f of x of lambda inside Vj cross Rn. So here x comma lambda is identified with x comma phi ij compose f of x lambda, and this gets sent under fi tilde to f of x comma lambda, and this gets sent under fj tilde to f of x comma phi ij compose f of x lambda, and these two are identified. So this implies that these maps glue together. To give a map, it is clear that f tilde is smooth and f tilde on the fibers is a linear isomorphism. Okay. So next let us check another similar thing. So now suppose we have two bundles E to Y and F to Y. And a map of bundles on Y, phi from E to F. Recall that this means that phi is a smooth map from E to F. Phi makes the following diagram commute. And the restriction to the fibers is a linear map. We claim that we can pull back phi to get a map of bundles over X. So this is also not difficult. So to see this, we may assume that there is an open cover of y over which E and F are trivial. Are both trivial. Then over each vi we have maps. We have smooth maps AI from vi to m cross n matrices. So here we are assuming rank E is equal to n and rank F is equal to m. So if E is given by transition functions phi ij and F by transition functions psi ij, then we have for y in vi intersection vj, we have this condition, the AIs and AJs, they should satisfy this intertwining condition. Phi ij y is equal to psi ij y. Compose aij y. So the bundles F upper star E and F upper star F are trivial on UI equal to F inverse VI and are glued using the transition functions phi ij compose F and psi ij compose F. And since AJ compose F, X of phi ij compose F, X is equal to psi ij compose F of X times AI compose F of X. So we can define a map of bundles on UIs using AI and check that these glue together. So thus we get F upper star phi from F upper star E to F upper star F. So one can do a further exercise which is left to the reader. Check that. So further check that the maps defined fit into the commutative square f upper star e to e, f upper star f to f phi, this f tilde, and this also f tilde. Let's say f tilde e, f tilde f. So the way in which we will use the preceding discussion is that if we are given a bundle E to Y and a global section, then since global sections are in bijection, with maps from the trivial bundle to E, this implies that pulling back, we get a map from the trivial bundle to f upper star E over X, since pull back of the trivial bundle is obviously the trivial bundle, and once again using the correspondence between sections and maps from the trivial bundle, so this implies we get a global section of f upper star E. Okay, so we will stop here.